Good evening, ladies and gentlemen. Welcome back to the Extraordinary Technology Conference 2017. This evening, we're going to be hearing from Cameron Rebigsol. He's going to be presenting the second half of his presentation that he wasn't able to finish earlier, Newtonian Gravitational Law over Dark Matter. Please welcome Cameron Rebigsol.
Thank you very much. Thank you. First of all, I would like to thank all the amazing people at this group. They give me the extra time for the presentation. You are all amazing too, by giving me your extra patience to share my view. Let me continue what I present this morning on the Newtonian gravitational law over dark matter. The dark matter concept is brought up by the Milky Way galaxy because people found that celestial objects moving at the edge of the galaxy is moving faster. It needs dark matter to explain this phenomenon. However, to me, if we apply the Newton's gravitational law more precisely, we don't need dark matter. In these two pictures, this bar and this point mass has the same amount of mass. And the flyby object A has the same distance from the center, mass center of this bar or for this point of mass. Between the two pictures, the flyby object A will receive a stronger gravitational force from the bar than from the point mass, although the point mass and the bar have the same amount of mass. With this extra or stronger gravitational force, we don't need dark matter because the force calculated from the bar is also applied through the gravitational law of Newton. What I did is I just break up this bar into infinitesimal point and then apply the Newton's law for the calculation. And then we get a stronger gravitational force over here. Continue from the previous bar, we move, suppose this flyby object is moving down at this point. Over here, this flyby object receives a weaker gravitational force than from this point mass, although the distance between them and the mass center of this bar are the same. If we need dark matter to explain the stronger force over here, what should we have? What should we come up to explain the weaker gravitational force over here? So dark matter does not warrant the explanation. Besides, I would like to call that gravitational force generated by this point mass as a normal force, but with a quotation mark. On the picture, suppose the flyby object A even move to the central division line of this bar. And again, this bar has the same mass as the point mass. But the calculation with Newton's gravitational law further shows that this gravitational force from the bar is even further reduced, much less than the gravitational force produced by this point mass. Okay, summarize from the previous analysis. we will have this phenomenon. When the flyby object fly by this bar and survive the gravitational pull from this bar, it will have a certain angular momentum. When it continues to fly over here, the angular momentum will not change, will keep the same. However, the gravitational force from this bar now is weaker. So the flyby object now should have excessive speed and then must fly away. We will... For the camera, switch, please. I'm sorry. Oh, okay. Okay, for a flyby object receiving a weaker gravitational force in this position, we will call it as an off-X effect. But on the other hand, when the flyby object stays at this position and receives stronger gravitational force from the same bar, we call this on-X effect. Suppose the flyby object flies from somewhere else, not from this position, but from somewhere else, and with enough angular momentum to survive the gravitational pull from this bar, when it moves to this location, symmetrical to this one, so at this position, the flyby object will receive stronger gravitational force. Now, starting from this position, coming over here, the flyby object will not have enough angular momentum or not enough centrifugal force to survive the gravitational pull from the bar, and it will get sucked into by this bar. With this effect, later on, I will explain that the Magellanic Cloud of the Milky Way galaxy is not a satellite galaxy of the Milky Way, but just a one-time visitor between each other, between the Magellanic Cloud and the Milky Way galaxy. In this picture, I place one vertical bar and one horizontal bar to make a cross. The bar concept is from the previous slide. In this situation, when the flyby object at this location, it will receive a gravitational pull not much different from a point mass. If this point mass has the same mass as the entire cross. Extending from the idea of the cross that in a previous slide, we will find that if the flyby object happens to be at the tip of the arm, it will, and if it survives the gravitational pull of the cross, when it flies over here, it will have excessive speed and move faster. However, very soon, when it moves over here, the gravitational force will be stronger again. So the flyby object will slow down its speed. And then when it moves over here, it's fast again, and then slow, fast, slow, fast, slow again. So compared to this situation, if you have an object B closer to the arm, and then object B has to fly with a higher speed in order to survive the gravitational pull from the cross. And going even closer, the object C has to have even higher speed to survive the gravitational pull from the cross. Okay, suppose those arms consist of loose material. And then naturally we can think that each material group closer to the center of the cross should have a higher speed to survive the gravitational pull from the cross, the mass center of the cross. If every arm is consisted of loose object, and then we will have a picture like this. And the cross at the center will spin at a very high speed. Okay, as far as our Milky Galaxy is concerned, in the old day, when the material fly all over to this location to form the material basis for the formation of the Milky Way, they will have the material, they will have a residual angular momentum to make the entire collection of material keep spinning about a mass center. Statistically, some material group may be more concentrated than some at some other area. Gravitational force and the statistic work together, and they will sense some material gathering on each side of the mass center or the entire collection. They will rather have a stronger gravitational force along a certain geometrical straight line. When they so spread in this manner, they will form a bar, although the bar is not solidly formed, but gravitationally, other material will feel this is a bar. Because it is a bar, the other material may gradually feel the on-X effect of the bar. And when they fly by over here, they will get pulled by the gravitational force from the bar and will not fly away, but stay with the bar. But when they stay with the bar, they will escalate the mass of this bar and make the bar even stronger on the gravitational force. Gradually, some material, like a group, this body A, it will not have enough angular momentum to follow the spinning of this bar, but keep dragging a little behind. But this bar has the strong gravitational force to drag this A to move along. And then another material even further away, like a B, it will go along with the bar, but drag it a little even further behind. And then same happen to C. As a matter of fact, at the other end of this bar, there may be the same situation. That's how a rotation arm or the called spiral arm is formed in the galaxy when the material collection is huge. However, there are also some material that angular momentum is really weak, such as D. So the fate for D will be two. Either get really sucked in by the bar, or because it will slip into the area where the off-axis effect is stronger. At this area, it has less gravitational pull from the bar, so it can survive with a slower angular momentum. But D is not the only situation like that. There may be some other material body like E, F, G. Gradually, there will be a ribbon, material ribbon, spanning from end to end along this bar. But the bar has two places, two regions that we can call off-axis region. One is on this side, another region is on the other side of this bar. That's how in the galaxy, Milky Way galaxy, we can find two bars spanning from end to end. This is called far 3 kpc arm. This is called near 3 kpc arm. That's how they are formed by flying object like a D. In this picture, our sun, solar system is about here. So with respect to the position we are in, this bar is farther, so it has the name far 3 kpc arm. But this arm is closer to us, that's why it's named near 3 kpc arm. At each end of the galactic bar, because of the on-X effect, it concentrates more material. That's how we see it here. And also, at each end of the galactic bar, we have a material ribbon extended at each end. So our galaxy has two spiral arms. That's how this ABC are forming the spiral arm. I've skipped this picture. Okay, with the analysis of the previous present, now we do find that two spiral arm feature among rotating galaxy are quite popular to us. Of course, you may find some galaxy with many arms too. However, given time, gradually, that bar will form itself, and then two rotation arms will gradually come into shape. In other words, our Milky Way galaxy has been quite old compared to those galaxies with many arms. But those arms are not really outstanding feature yet. Okay, we come to this point to claim that the Magellanic Cloud cannot be a satellite galaxy of the Milky Way. Suppose this is the Milky Way disk. If we view this Milky Way disk edge on, we also see a bar. Suppose the Magellanic clouds survive the pulling of this bar. Now with the angular momentum it survived, it moved over here. It is in a region of off-axis effect. That's how they are now. And at this position, but with the angular momentum, they survive the gravitational pull. They now have excessive speed. If it further moves down here, but not yet, okay, on the picture, but not yet. But if they move down here, they definitely have excessive speed. They will be flying away from our Milky Way galaxy. At this position, indeed, nowadays, observation shows some some astronomers do believe that they already have too much speed flying around to be a satellite galaxy of the Milky Way. So without dark matter, we can explain the formation of the 2 rotation arm and the 3 KPC arm, and also with that analysis, we can assert that Magellanic Clouds will not be a satellite galaxy of Milky Way. But with dark matter, I don't know how this can be explained. That's all my presentation, and thank you very much for your patience. Thank you. Thank you very much.
Thank you very much, Cameron Rebigsol.
Yeah.
That was fantastic. Thank you.
Thank you very much. Thank you for your extra time.
All right, we'll see you all back here at 7 o'clock. Thank you for your patience.